Hello there, a new day, the same old project. What I'm trying today is to replace these wires with a very strong one. You see, I got 3 wires here. They are all in parallel just to keep ohms, the resistance as low as possible, but it's still not enough. The MPPT part of the inverter is getting confused because these three appear like a kind of resistor, on fluctuation ups and downs. So for the beginning, I'm gonna take this out and replace it with something new. I'll show you in a second. So here I have my clamp meter. As you can see now, we have 13.3 amps running through these wires all in parallel. So I don't say that it's such a big impact, but anyway, I'll take this down and check for the resistance. Different cables here. So this is a 16 square millimeters AVG. I can't use this guy. Okay, so this one says it's running to 8. Okay, so it will be AVG 8. Okay, we have AVG 6, so it's not running on this, but it can be helpful. 3 meter and 16 centimeters. So we got 316 centimeters. How comes they sold me 16 centimeters more? Amazing. Never happened. Usually it's less. Okay, so we are maximum open here. Let me try to get into the... No, it's way too big, but we can try that. And the other side, it's working like that too. So that proves it's a true 6 AVG. Let me have my special low resistance meter, and I'm really curious about results. This is a special instrument. It's measuring in 4 points, injecting an 1000 hertz into the cables. 4.5 milliohms. 4.5 milliohms. AVG 6, 316 centimeters. I think this guy it's 2.5, like gauge 10. Does it say anything here on the cable? 9 AVG, that means like 10 square millimeters. Okay, so how much do we have here? Let me measure that. 2.7 centimeters in length. And now let's check for the internal resistance. Okay, 11.28 milliohms. Okay, that's 9 AVG. I'm not sure. I think it's 8. And the last one here is this guy. We just saw it in action. So let's measure this. And we have like 4 millimeters. How long is it? 230 centimeters. Now let's check for the resistance, and we have 532. That's it. And we got like 5.32 milliohm. Okay, so here we have the results. AWG AVG 6, 100 meters, 0.142 ohms. 100 feet, 43.29 milliohms. AVG 8, 100 meters, 0.231 ohms, and the same number, 100 feet, 70.42 milliohms, and AVG 10, of course, 10 at 100 meters, 520 milliohms, and 100 feet, 158 milliohms. Okay, so these results are real field, reality. So these are cables, you can buy them in the shops. Of course, they are not at all the way it's supposed to be. Maybe 20% tolerance, even more. Okay, now I found here at www.mayfield.energy this interesting formula. VD is the voltage drop percentage, exactly what we need to know. Voltage drop, then we can calculate the power loss. If we use this formula from the page I just show you. So we have the volt dropped in percent equals, let's say, 2 times the length, in our case 100 meters, and then times 20 amps, okay, and times 0.142 ohm for the first part of the equation. So we have times 20 and times 0.142, and that gives 568. Then 568 divided by 1000 and divided by, let's say, 60 volts, we have the voltage source equals, and now times 100, and so we are losing in fact 0.94%. We'll have a 56.4 volts at 20 amps at the end of the 100 meter cable. Okay, so we are losing like 3.7 volts. All right, power equals voltage times current. In our case, we have like 0.564 times 20 amps. With a loss of 0.5, we have 11.28 watts. This is the result. That's for gauge AVG6. Now, let's do the same for AVG8. So, we are losing 11.8 watts. Pretty okay for 100 meters of cable. Divide that by 3 and you have the numbers in feet, around 3 point something watts. Okay, let's do the same for AVG8, which have a different resistance. So let's say 2 times 100 times 20 times resistance 0.231, and we have like the first number 924. This one gets divided by 1000 and divided again by 60 and 100 times. That means 1.54% of voltage drop. This is percent of voltage drop. Now simply we take 60 volts divided by 100 and then times 1.54, and we have a 0.924 volts voltage drop. And simply now we can 0.924 times 20, that's the amps, and we have a losing of 18.48 watts for this kind of cables. And what about AVG10? Let's do the first string. 2 times 100 times 20 amps and times 0.520 divided by 1000 and again by 60 times 100, and that means a 3.46 volts dropping. That's percent. 60 divided by 100 and times 3.46, that means let's say 2.076 volts dropping. Okay, now we can very easy have the formula again. Power equals voltage times current. So we have 2.076 times 20. So we are losing 41.52 watts of power, of course, at 100 meters of cable. And I can tell you 100 meters or 315 feet or something, that's nothing. Because if you count all the cables you have in solar install, then you'll find some some long parts of that. These resistance are for real. These are cables used, and these are facts. Okay, I hope it's useful. Don't forget, like, subscribe, and have some fun. See you. Bye bye.